In this video, I'll talk about gas pressure. First, what is pressure? If a force is exerted on a surface, the pressure this surface feels is equal to the force divided by the surface area. Pressure equals force over area. What about gas pressure? It results from the collisions between the gas particles and the surface of the container. So what gas particles? Well, it can be oxygen, nitrogen molecules. It can be helium, argon atoms. Let's Control-click this link to see the simulation of the gas particles. I downloaded this program provided by Wolfram on my desktop, so we're going to take a look at it. And we can see a bunch of particles moving around. They collide with the surface areas of this cubic box. We are looking at the two-dimensional cut view of this box. The pressure is 10 without a unit, because we just need to understand how pressure changes with the number of atoms, temperature, and volume qualitatively right now. You can tell the pressure goes up and down because pressure is a statistical average of all these pressures exerted by those gas particles. And then I will change the number of particles from 35 to 140. I'll let you predict how the pressure will change. It goes up to roughly 40. So I increased the number of atoms fourfold. The pressure increases fourfold. Now I will reduce the number of atoms back to 35. The pressure drops back to 10. Now I will change the temperature from 0.04. Again, there's no unit here. To maybe 0.08. I will double the temperature. I'll let you predict how the pressure will change. Remember, when temperature goes up, the particles move faster, because temperature is a measure of the average kinetic energy. So I'm going to hit the enter. You will see how the pressure changes. It goes up to roughly 20. So if we double the temperature, the pressure is also doubled. Pressure is proportional to temperature. Now I will bring the temperature back to 0.04. The pressure should drop back to 10. Now I'm going to change the container size from 0.3 to 0.6. What do you think? How will the pressure change? This time, just imagine when the container gets bigger, the number of atoms remains constant, the temperature remains constant, the speed or the average kinetic energy of the particles remain constant. And then we have a larger container. It will take much longer for those particles to collide with the surface area. There's a longer distance between two successive collisions. But anyway, I doubled the size of the container. Let's see how the pressure will change. The pressure drops. Now I will increase the size of the container, and then you can see the pressure increases dramatically because I'm using a very small container size. Now I'm going to use a very large container size. And you'll see the pressure drops dramatically, and you can see it takes much longer for those particles to collide with the surface areas now. I'll change it back to 0.03. 0.3. Okay, this is the original value. Now the pressure is roughly 10. And you can see the pressure actually, it's not a straight line, it goes up and down. Again, this is because when we are measuring pressure, it's the average value of those random motions and random collisions of the gas particles. However, if we have an infinitely large number of particles, eventually the average is going to even out to be a constant, and you can see this straight line is our theoretical value, assuming we have an infinitely large number of particles. It's going to be a straight line, the pressure is going to be constant. Now let's get back to the gas pressure and its unit. The SI unit of pressure or gas pressure is Pascal. 1 Pascal is 1 Newton over meter squared, and we can convert that to 1 kilogram divided by meter divided by second squared. I'll let you do this. Commonly used non-SI units of pressure include 1 bar. 1 bar is 100,000 pascals. Bar is the UPAC standard pressure since 1982. And we have ATM. 1 ATM is 1.01325 times 10 to the power 5 pascals. And this is the air pressure at sea level. 1 ATM is the standard pressure before 1982. It's still considered standard pressure in some of the textbooks. 1 ATM is roughly 760 millimeter mercury or 760 torrs. 1 torr is 1 millimeter mercury. So if you look at this mercury barometer, the height of the mercury is 760 millimeters or 0.76 meters. This is because there's an air pressure difference exerted on this level, this red line. It's 1 ATM versus 0, so there's a pressure difference from the air. And also there's a pressure difference because of the height of this mercury. And later we're going to compute this height. 1 ATM is also 14.7 psi. Your tire pressure is typically between 30 to 35 psi. And 30 to 35 psi is roughly 2.1 to 2.5 or 2.4 ATM. So you can just use 30 divided by 14.7 or 35 divided by 14.7 to get the value in ATM. Now let's look at one example problem. We're going to prove 1 ATM is roughly 760 millimeter mercury. How do we do this? We need to look up the density value of mercury, which is 13.56 kilogram per cubic meter. This is a really big number. Remember, water has a density of 1 kilogram per cubic meter. The gravitational force of this mercury is simply the mass multiplied by the gravitational acceleration. So we have the mass here, the density times the volume times the gravitational acceleration, and this number gives you the force exerted by the mercury column to this red surface area. And then this red surface area also feels the pressure from the air, which is the air pressure, 1 ATM, times the surface area, A. We do not need to know what's the value of A. A is cancelled. And then the remaining calculation is simple. We just compute this H, and the result is 0.76 meters. Actually, if you consistently use SI units, you don't have to worry about unit cancellation, simplification. In the end, it's going to be the SI unit of the length, which is meter. Now, I'll give you a practice problem. I want you to prove 1 ATM is equal to 14.7 psi. PSI is pound per square inches. What you need to do is you need to use this pound to compute the gravitational force. 1 pound is 0.4536 kilogram, and 1 kilogram is equal to 9.806 Newton, and 1 inch is 0.0254 meters. 1 square inch is 0.0254 squared meter squared. Therefore, all you need to do is you convert this to Pascal first. It's going to be 14.7 times 0.45 0.536 kilogram per pound, multiplied by 9.806 Newton per kilogram, divided by 0.0254 squared meter squared, and then you will get 101,000 pascals, which is equal to 1 atm.